welcoming Dr. Vasanth Kumar, an accomplished researcher with experience in material synthesis, electrochemistry, and advanced characterization. He is currently a postdoctoral researcher in the National Autonomous University of Mexico. He has an extensive experience in analytical techniques such as NMR, SEM, TEM, XRD, FTIR, etc. His research spans various areas, including sustainable material, catalysis, and electroplating. Dr. Vasanthakumar will be giving us valuable insights into the NMR spectroscopy today. The class will be for 60 minutes, and there will be a question answer session at the end of the class. So now I humbly welcome Dr. Vasanthakumar to handle this session.
Thank you, Shambhu. This is my actually a privilege to have such a session and then to enlighten the audience. I'll do my best to make them understand and tell informations about the NMR spectroscopy. So, and I'll share my screen and so can someone confirm me if the screen is visible?
Yes, doctor, it's visible.
Yes, it is visible.
Yes, thank you. So So before I start, as I said, I would like to thank the organizing committee for reaching out to me and then extending me this opportunity to present on the introduction to nuclear magnetic resonance spectroscopy, which in short it is called as NMR spectroscopy. This NMR spectroscopy is a widely used technique and it is kind of a basic characterizations for an organic chemistry or an organic molecule. So in this presentation, I'll be trying to cover a majority principles of NMR and make you understand what is NMR and how it can be useful and how to, with an NMR data or NMR spectra, how can we arrive at a chemical structure because NMR is a very powerful tool to do that. And in case I'm exceeding the time limit or I would request the organizers to remind me 10 minutes before so that I can cut short it if it is needed. So this presentation will be around for 1 hour. So we'll have around 60 slides to cover these sessions. So this is completely introduction to an NMR spectroscopy, which is nuclear magnetic resonance spectroscopy. So and I also request the participants to raise the questions whenever you feel you're not following or you want me to slow down or move faster. You can always it is always welcome. So as you see here, the NMR spectroscopy is an important tool for finding out the structure of an organic molecule. The structure you see here is the glucose molecule. So this is a simple organic molecule in which everybody uses it. So, but if you could see the structures clearly, this is a chiral molecule. The NMR spectroscopy is so sensitive that it can detect two different chiral molecules. And the NMR spectroscopy is based on a principle called as angular momentum, or it is also called as the nuclear spin. So it is based on a principle called as the angular momentum or a nuclear spin. And then the medical application of NMR comes here in the MRI spectroscope, imaging. So MRI imaging is the alternative term that is used in the medical terms to understand what is an NMR. So the presentation will have three sessions. One is the introduction. The other, I will discuss few examples of the proton and carbon 13 NMR, like how to solve it and what are the key features in the NMR. And then I will also have examples of spectra of proton, carbon, phosphorus, and nitrogen. And if time permits, then we will also move towards fluorine and 2D NMR spectroscopy. So introduction. So the NMR is a spectroscopic technique. As I said before, it is very important for an organic chemistry to understand the structure of an organic compound. If we could see here, there is a lot of organic compounds. Here is a butane, cyclopropane, benzene, and everything. But when we look at the chemical structure, what we see is just the carbon-carbon bonds, but the NMR concentrates on two important nuclei. One is the hydrogen, the second is the carbon. There are also other nuclei which are also NMR active, but on majority of the NMR is recorded either on a hydrogen, or in terms it is called as a proton, or in terms it is called as a carbon, which is also called as carbon-13 NMR. We all know that the carbon-13 is also a very important technique to understand the age of a substance like carbon. They call it carbon footprinting. So carbon footprint also uses the technique of NMR, the C13 carbon nuclei, to understand the structure and then the age of the population of the carbon spectra. Also, NMR studies gives how many number of magnetically distinct atoms are present in the molecule. It does not just gives the number of protons or number of carbon, but it also gives the number of magnetically distinct atom that is present in a molecule. So as I said before, the populars are proton and C13 NMR. So by which it can be we can use to find out the structure of an organic compound. Okay, so mainly the organic to find the structure of an organic compound, NMR, and then with the support of an IR spectroscopy, it is possible to determine the organic structure of the organic compound very easily. And people have extended this technique not just only for the simple organic compound, but also a complex organic structures like the proteins and then the DNA structures. So the images you see here is also the protein and imaging structures. Which shows that which has been solved by nuclear magnetic spectroscopy. So as I said before, the structure of the D glucose and L glucose can also be separately studied using an NMR spectroscopy, and then one can find which is one can find the chiral molecules, chirally active molecules also in an NMR. So before we go and understand the how NMR works, I want to remember we have all seen such an magnetic when we take an iron filings, so the iron substances or an iron dust, and then it attracts by a magnet. So the NMR is the same principle. So when we have an atom, and then when we apply an external magnetic field, the external due to the presence of an external magnetic field, the nucleus of an atom aligns towards the magnetic field. So this is the basic principle of an NMR spectroscopy. So this is let's assume like this is the nucleus of an atom. So when we have a nucleus of an atom and there is no external magnetic field, it is called as a ground state, or it has its own spinning around it. So the nuclei is electrically charged. We know the nucleus has got protons as well as neutrons, and this is electrically charged, and thus it behaves like a small magnet. So thus it behaves like a small magnet. So when you try to apply an external magnetic field, there is two possibilities. One, the small nuclei which acts as a magnet can align with the magnetic field. So this is the direction of the magnetic field, or it can be opposing of the magnetic field. So when it aligns with the magnetic field, it is called as a high spin structure. Sorry, when it aligns with the magnetic field, it is called as a low spin structure, or when it is in the opposite direction of the magnetic field, it is called as the high spin energy state. So this is the higher. So we have a nuclear magnetic spin, and this magnetic spin, when it is in direction, we could see this arrow is in the direction of the magnetic field. So this is called as a lower energy state. And when you have it in the opposite direction, this is called as a higher energy state. So according to the external magnetic field, or according to the direction of the external magnetic field, the nucleus of a magnet or the nucleus of an atom tries to align itself either in the with the direction or in the opposite direction. So this is also an illustration which shows this. So before applying any magnetic moment or a magnetic field, the nucleus will have a random magnetic direction. So once you apply a magnetic field, all the nucleus tends to be in a direction or in an opposite direction. So it depends on the nucleus to have. And after we align an external magnetic field, what do we do is we tend to pass an radio frequency, and this radio frequency tries to flip. For example, the magnetic field is along the x direction. So then let's assume that the nucleus aligns in the magnetic field. So when we apply a frequency, the magnetic tends to align in the z direction. And after we remove it, it comes for a relaxation, and this is called as an excitation. And after the radio frequency is stopped, it comes to the relaxation position, and which is called as a free indexed free induced decay, and this decay gives us the signal of an NMR spectra. So this is a beautiful illustration which will help you to understand it. Suppose, let's say that at this point, at a particular point, when there is no magnetic field or when there is an external static field. So when we have an external static field, you would see that it aligns in a precise way in a small direction. And when we resonate it with an radio frequency, the red color one is the magnetic field of the nucleus, which tends to move around in a specific direction. So that is because only when we apply a radio frequency. So therefore, during an NMR measurements, we apply a static magnetic field, also a resonating magnetic field. So the resonating magnetic field is in the form of a radio frequency. Yes. So, and this diagram is a very popular for the NMR spectroscopy, which shows the precise orbital. So, which means that when a nucleus is forming, when a nucleus is there, and then when you try to apply a magnetic field in a z direction, which is perpendicular to it, the nucleus tends to rotate it because it is also acting as a small magnet. So therefore, it tends to rotate, and this is called as an spinning nucleus, which is in direction with the external applied magnetic field. And when we talk about this magnetism, so people are often confused with the paramagnetic and diamagnetic structures with the NMR. So to have a simple rewind, so paramagnetic is the presence of an unpaired electrons. Unpaired electrons in an atom gives rise to something called as a paramagnetic. And when you do not have an unpaired electron, it is called as a diamagnetic. Okay. And this paramagnetism and then the diamagnetism is not at all related to NMR spectroscopy. Though most of the NMR active atoms are diamagnetic, but there are also atoms like uranium 3 plus, Fe3 plus, Fe3 plus. All these are also paramagnetically active, and people have also find out an NMR method which is called as a paramagnetic resonance, nuclear magnetic resonance spectroscopy. So paramagnetic NMR, they also call it. So therefore, an atom can be a paramagnet and an atom can be a diamagnet. Both of these can be NMR active. So to be in simple terms, NMR activity depends on the nuclear spin. So the NMR activity depends on the nuclear spin, which is called as an I of the nucleus, and the nucleus with the non-zero nuclear spin, which is equals to 0 or NMR active. So when the nuclear spin is not equal to 0, then the substance is NMR active. It doesn't matter if it is a paramagnetic atom or a diamagnetic atom, because the paramagnetic and then the diamagnetic property comes out from an electron, whereas the NMR is a technique which measures the nuclear spin. So we are talking about a nucleus and then the external electrons. So the paramagnetic and diamagnetic character comes from the external electrons, whereas the NMR studies the nuclear spin. So now we are talking about a non-zero nuclei. What is this non-zero nuclei? So we know that the nucleus contains something called as a proton and then a neutron. So the number of protons are called as atomic number, and then the number of neutrons combined with the number of protons are called as atomic number. So number of protons plus neutrons, number of neutrons are called as mass number. So when we have an atomic number is even and then the mass number is even, then the nucleus will have a spin of I0. So therefore, the spin quantum number of the nucleus will be 0. So therefore, when an atomic number and then the mass number is even, the spin I equals to 0. Therefore, it is not NMR active. When the either atomic number or the mass number is even or odd even, or odd odd. So all these three combinations of even odd even, and then odd odd will give rise to an active NMR nuclei in which the spin quantum number is not equals to 0. So this is what a most important thing that we have to learn. So when we look at look at an atom, if the atomic number is even and then if the mass number is odd, then it is NMR active. If it is even and then mass number is also even, then it is not NMR active. And we all know there is something is called as an there is something called as the proton and then the deuterium. So these are called as isotopes, and then the tritium. So these just differs by the atomic number and mass number. The number of protons and neutrons differs in the isotopes. So therefore, in some cases, few isotopes are active and few isotopes are not NMR active. Yes, as I said about the spin quantum number, the spin quantum number is represented by a capital I. So this is a physical constant, so which tells us how many number of spin states an atom can have. So we can calculate it just by a small numerical equation, which is called as 2I plus 1. So if we have I equals to, let's say like the capital I is equals to half. So when the spin quantum number is half, then the total number of allowed spin states will be, so the total number of allowed spin states will be 2 into half plus 1. So these two gets cancelled. So therefore it is 2. So for an atom which has a plus half as the quantum number I, then the number of spin states are 2. So what are the number of spin states of 2, which is like plus 2, plus half, and then minus half. And then so the number of values from the value can be from plus I to minus I. So if I have plus half, then it will be like plus half and minus half are the two allowed spin states. Okay. So now when we have the spin quantum number as 1, and then we'll have number of spin states as 3. In case of carbon 12 6, the spin quantum number is 0. Therefore, the number of spin states allowed is also 0. Therefore, this is not an active molecule for NMR. Similarly, here it goes for oxygen. So the oxygen 16 8 is also not NMR active, whereas the carbon 13, nitrogen 14, oxygen 17. So the oxygen 16 is not active, whereas oxygen 17 is active. And then we have got 19 fluorine and then phosphorus 31. So these are the common nucleus. These are NMR active in nature. And below are the number of spin states these nucleus can have. As we said before, the proton is the one of the popular nucleus to studied. So therefore, we'll discuss more about the proton and understand the spin properties. As we said before, protons have got two spin allowed states. One is called as the plus half, the other is called as minus half. So the plus half arises when it is in with the direction of the external magnetic field. When it is with the opposite to the direction of the magnetic field, it is called as the minus half. So these are the two allowed configurations. And then the plus half is usually represented as a clockwise direction, and then the minus half is usually represented as an anti-clockwise direction. This is for an to understand the spinning of the molecule. So the nuclear spin state, which is plus half, is called as the lower energy since it aligns with the magnetic field. On the other half, if it is minus half, then it is called as the, when it is in opposite direction to the magnetic field, it is called as the lower energy state. Okay. So when an external magnetic field is applied, it should be either plus half or minus half. So without the magnetic field, so without the external magnetic field, both the spin states, plus half as well as minus half, are degenerate, which means the energy of them are same. So when an external magnetic field is applied, the energy of them is, one is raised up, one is raised below, and this is called as plus half and minus half. And how much it is reduced, the magnitude of the separation is given by the frequency applied. So let's say that if you have a magnetic field and then from here the energy goes up, and then the one more is the minus half, which is energy goes down, and this is equals, this energy difference is equals to the h nu, and this h nu is the applied frequency in the magnetic spectrometer. Yes. So in an NMR machine, we do apply an external energy in the form of a radio frequency, and this radio frequency is precisely a quantized process, which means the atoms or the nuclei observe a certain amount of energy, and it does not depend if we have more energy, it is going to absorb more. So this is a quantized process. So the plus half is always constant irrespective of how much of energy it gives. So it is that how much of energy is observed by the nucleus is always a quantized process. So that is what I wanted to stress upon here. So the stronger the applied external magnetic field, greater would be the difference between the spin nuclear states. So before we go to an example, I want you to understand few concepts. So because these are called as these are very simple but important concepts to understand the NMR spectroscopy. So the first concept is called as magneto-gyro ratio. It is very simple. It is the difference in the charge and then the mass. So when you have a nucleus and then each nucleus have got different number of protons, therefore it has got different amount of charge, and each nucleus have got different number of This is charge corresponds to protons and mass corresponds to number of neutrons. So since the number of protons and number of neutrons for each nuclei is different, the ratio of this is called as magnetogyric ratios. So this ratio is called as a magnetogyric ratio. So because of this ratio, the electron has a spin around its own axis. Sorry, the nucleus has a spin around its own axis. And this spinning around its own axis is called as laminar frequency. So the frequency in which it is spinning around its own axis, like a Earth or a moon, which also spins around its own axis. So this is called as a laminar frequency. Okay. So because of this frequency, there arises a parameter which is called as an angular frequency. So because of the magnetogyric ratio, there happens a spinning because it is a small magnet without applying any magnetic field. It without applying any external magnetic field, it also has in its own inherent angular frequency. So when it has an inherent angular frequency, and when you try to apply a radio frequency wave to this, and this both have to couple each other, and because of this coupling, there is an energy state differences. So when there is an energy state differences because of the applied magnetic field and then the inherent magnetic field, and then it is called as a nuclear resonance. So when these both energies are in a coupled state or in which matches each other, there arises something is called as nuclear resonance. So we have an internal magnetic field, and this undergoes a precession or a rotation, and this is called as a laminar frequency. And because of the laminar frequency, there arises a certain compound called as an angular frequency. So when this angular frequency and then the applied radio frequency wave are in in resonance or in line with each other, it generates a nuclear resonance. So that is why the name of the spectroscopic technique is called as a nuclear magnetic resonance spectroscopy. Yes. So this diagram gives us a clear intention. So here we see that, as I said before, when we apply a static magnetic field, the spin of an electron, the spin of the nucleus is changed. And when you try to apply a new magnetic field in the form of a radio frequency, it rotates on its in a different axis. Because it rotates in a different axis, this is called as a nuclear resonance. So now we have seen something about the principle of the and how does the nucleus act as a small magnet, and what is the influence of the nucleus in the presence of the external magnetic field. We'll go and see how this instrument is built. So usually this is an NMR tube or a sample tube for an NMR. So we would fill some solvents inside it. So we will have an organic compound dissolved completely without any residue, and then it will be filled inside it. So what is the level in accord it can be filled? It can be filled until like 1/4 to half. So when we have a tube, the maximum you can fill is half, but you can fill a quarter of the sub tube, that is even sufficient for the NMR spectra to be recorded. Okay. So when we have this is a simple glass tube, and this simple glass tube is a very narrow glass tube, and inside this we fill the a solvent along with the substance dissolved in it, and then there is something called as a sample tube. So this is also called as a sample tube, and the what you see here is a sample holder. So this is a small module that fits into the sample holder. So there is this is a little heavy, and this is made up of rubbers usually, so that this is heavy and fits in here. Okay, and this goes inside this tube. So this whole thing is an NMR machine. And this is usually a free floating machine, like it is not placed on the ground to avoid the temperature fluctuation. And there is a strong magnet present inside this. So it is a superconducting magnet. And these magnets are usually present inside the liquid helium temperature. At liquid helium, there is a liquid helium around surrounding these magnets. And to prevent the liquid helium from evaporating, people use liquid nitrogen to prevent the helium from evaporating. So because liquid helium is a very low temperature, but whereas liquid nitrogen is comparatively cheaper as compared to the liquid helium. Therefore, they use liquid helium as well as liquid nitrogen to maintain a temperature which is suitable for the superconductor. So we have an NMR tube, and this goes into the center of the NMR machine. And then we have an NMR console, which controls the radio frequency, magnetic field, and then the pressure, and then the number of times it has to be recorded. And then we will have a workstation or a computer that would record the NMR spectra and help us to analyze it. Okay. As I said before, this is the tube. This is an NMR tube which is made up of a glass, and then the coil of the NMR coil will just affect 1/4 of the tube. So therefore, it is required to have a concentrated solution, which is just 1/4 of the tube. And so this is so this was an actual picture. And when what we see here is the pictorial representation. So we will have a sample tube inside, and then surrounding the sample tube. So we will have a sample tube here, and then surrounding the sample tube, we'll have an magnet, which can be controlled, or which is a superconducting magnet. So therefore, the magnetic field of this magnet can be controlled, which can move higher or smaller. Okay, and then this magnetic field is called as a sweep generator. So which means that it can generate a certain amount of magnetic field from a lower energy to a higher energy magnetic field. So, and then we also have a RF transmitter, so radio frequency transmitter. So in from one side, and then the radio frequency receiver and detector is on the other side. And then the recorder is usually the computer system, which records the NMR spectra. So the first and important parameter for an NMR mission is the magnet. So this is a permanent magnet or an electromagnet. Both are used in the NMR spectrometers. In a small missions, like when we have a smaller frequency, we use a permanent magnet. When we have a larger mission and which needs a lot of energy, so we use a electromagnet to control the magnetic field around it. So the homogeneous magnetic field is applied throughout the sample, and this is applied just by spinning the sample tube. So we have a sample tube here, and why this is heavy. So a sample tube is fit with a module, and this module helps us to levitate the sample, and then it spins around by supplying an air current. So that is what it is given. So when we supply an air current, the sample gets an uniform magnetic field around it. So therefore, the sample has got similar magnetic field throughout the system. And then the sweep generator, which helps to adjust the magnetic field continuously and precisely over a small range as well as a broad range. The other part is the sample holder. As I said, the sample holder is responsible to keep the sample in between the two poles of a magnet. Also, there is a air current which flows and then which levitates the sample and spins around it, so that each part of the sample or every part of the sample gets the uniform magnetic field. And also we have a radio frequency generator, and usually NMR machines are termed in terms of megahertz. So when we talk about an NMR machine, they call it like it is a 300 megahertz machine, 600 megahertz machine, or a 30 megahertz machine. So this is the frequency in which the machine is used. So when we apply a magnetic field, the nucleus aligns towards the magnetic field, but how fast then the nucleus can be spinned around depends on the radio frequency generator that is available with the mission. So therefore, radio frequency is also an important part of an NMR mission, and then each NMR mission is labeled with the radio frequency. So the typical radio frequency that we would see around in the institutes are 100, which is a lower precise one, and 300 or 500 is the high standard ones. So 300 or 500 is the standard one, and 100 is the lower frequency mission. So the other parts are radio frequency detector and recorder. So the radio frequency detects the radio frequency change that is happening in the NMR sample or the sample of our interest. And then the recorder and integrated is usually the computer system which records. And then the x-axis is the strength of the magnet, and then the y-axis is the intensity. Now, if we come to sample preparation, the sample preparation involves three small steps. One is like the sample of interest should be an organic compound, or it should be a soluble compound. First condition, and we have to take some very small quantity like 10 to 20 mg of a dry sample. So there should be no other solvent present inside them, only the sample in the form of a dry. No external solvents, no moisture, no impurities are preferred. Second is and we have to choose a suitable NMR solvent. There are a lot of NMR solvents. We have to choose a suitable NMR solvent in which the sample is readily soluble, or it can be solubilized clearly. Okay. So if it is not soluble, people also add a mixture of solvents. In case of in case like, for example, if you use chloroform, people often use DMSO D6 along it. So that it is clear solution, because only this clear solution has to be transferred into the NMR tube. There shouldn't be any undissolved or a residue which should be present inside the NMR tube, because it is going to give a lot of noise in the spectra. So the samples amount is also so small. So therefore we have to add only a clear substance. So if you have to make a clear solution, either you can have a mixture of solvents, or we can heat the substance so that it is completely soluble. And then in case if it is not soluble, we'll have to filter it through a small filter paper and then transfer it to an NMR tube. Okay. So the popular solvents used for the NMR are carbon tetrachloride. So this is actually a cheap and an aprotic solvent, so which have a proton inside them. So, but it is also highly corrosive. We all know the carbon tetrachloride is also very corrosive. So people do not prefer carbon tetrachloride. The most popularly used NMR solvent is the deuterated chloroform. So the chloroform is CHCl3, and then when you deuterate the chloroform, it is called as a deuterated chloroform. So this helps in the soluble of makes most organic compounds that are soluble. And since this is also an aprotic solvent, so since this is a protic solvent, it has got a good dipole moment. So most organic substances are soluble. And one more important advantage of using this carbon chloroform D is that chloroform D is volatile. So therefore you can recover whatever substance you have dissolved. And then NMR is a non-destructive technique, which means like after measuring it, the samples can be recovered back if you just evaporate the solvent. So therefore chloroform D is used for a substance which have got small quantities, and then you need to recover the substance. So for those kind of sample, chloroform D is used. So in some cases, the compounds are sparingly soluble. So therefore, they also use a mixture of DMSO D6 in order to have the NMR spectra. And also, the chloroform D doesn't have an NMR signal, but this chloroform D will not be 100% pure. So therefore, there will be some impurities present inside them, which will give signal at 7.2 delta. So at 7.2 delta, this delta is given by here. In the forthcoming slides, I will explain you what is delta. It gives some peak around 7.2. The other solvents are DMSO D6. So this is a highly oxidizing and a good solvent. So this is helped for dissolving heterocyclic compound. And then DMSO D6 comes with the water impurity. That's what it has given. So there is a lot of water impurity which comes. Suppose in case you need an highly polar solvent, then the next choice is called as the methanol D. So therefore methanol is highly polar in nature, but it also helps. It also comes with an impurity of residual peaks of methanol as well as water. So therefore we will have a solvent peak in the NMR spectra at 4.8 and 3.3 also. Also, this deuterated solvents of methanol can also substitute functional groups like alcohol, amine, and COCl, CONH2. The other popular solvents are D2O, which is the deuterated water, or we can also call it heavy water. And this gives a residual peak around 4.9. And then deuterated benzene. So they call it C6D6. So this deuterated benzene is also very corrosive and carcinogenic in nature, and this gives a standard NMR signal at 7.27. The other very corrosive substance is called as a trifluoroacetic acid, and this trifluoroacetic acid is a very uncommon solvent that is used for the NMR spectra. In case this substance is not soluble in any of these liquids or solvents, they use trifluoroacetic acid, because if it is a heterocyclic compound or a polymeric chain, so they need to use an higher polar solvent. So that the choice is that trifluoroacetic acid. And one more important thing is that the sample should be 100% clear. There should be no insoluble substances or a small solid should be present inside them. It is not advisable, and the NMR solution should be 100% clean. So to prevent the NMR solution to have some residues, people usually filter it through a filter paper and then take only the clear solution. Okay, so now we saw about what is the principle of NMR, and then we saw about what are the instrumentation technique and what are the solvents used for the NMR. And when we see a signal, so when we have an NMR spectra, how do we solve the NMR spectra? And what are the informations that we look into an NMR spectra? There are four information that we have to look into an NMR spectra. The first thing is called as the number of signals or the number of peaks. The second is the position of a signal. So where is the position of the signal? Second is the intensity, which is the height of the peak. The third is something is called as a splitting. So a single peak in an NMR can be split into multiple peaks. So that I'll explain it shortly. So here is an example of a spectra. Excuse me. So here is an example of NMR spectra. If you see here, as I said, the first thing we have to see is the number of signal. In this case, this NMR spectra has got two signals. One is around 4.2, the other is around 5.5 or 5.6. So these are the two number of signals. Okay. The second thing is the position of the signals or the position of the peaks. So this value is very important because the value of the peak or the position of the peak tells us what is the chemical nature of the. So the position of the peak tells us the chemical nature of the peak. Okay. The second thing is the intensity. So the intensity tells us the number of hydrogens that is attached to it. If it is one hydrogen, you see the intensity is smaller. If it is two hydrogens, here we have got two hydrogens, so it is double the peak, double the size. So therefore, the number of the intensity of the peak tells us an important information about the number of hydrogens or the protons present inside them. Okay. So we have seen number of signals, the position of the peak, intensity, and then the splitting. So in NMR spectra, there is something is called as a splitting, which means one peak is split into a different peaks. For example, this peak around 5.6, 5.7 is split into a three peaks. So this is called as a triplet. So the peak around 4.2 is split into two. So this is called as a doublet. So this is called as a doublet and this is called as a triplet. And in the forthcoming slides, we will see why it is split and what are the different splittings. So, but whenever we look at an NMR spectra, these are the four important things that we have to see. One is the number of signal. Second is the position of the peak, which means the value, which is called as the delta or parts per million, and then the intensity and then the splitting. So SPIS. So these are the four informations that we have to see to understand the structure of the organic compound. So here in this compound, you could see this is called as a proton NMR spectra. So therefore, it measures only the chemical nature of the hydrogens. Okay. So before we go into an actual spectra of a different examples, I wanted to understand one important concept, which is called as equivalent protons. So the number of signal, the first idea is to look at the number of signal. The number of signals depends on something called as equivalent proton. The first example we see here is a methane. So there are four hydrogens in the methane. So each hydrogen is attached to a carbon. So when we talk about a chemical equivalence, so each hydrogen is similar. So there is one hydrogen and at an equal distance, there is one more hydrogen. So therefore, in all four directions, the hydrogens are chemically equal in nature. So therefore, how many number of peaks we will have? We'll have only one NMR signal, which would be corresponding into four hydrogens. Similarly, this is for methane. In case of ethane, we would see there would be like six hydrogens which are chemically equal. So therefore, we will have one single peak which corresponds to six hydrogens. Similarly, there is one more compound which is called as tetramethylsilane. So this is called as an TMS. So we will call it TMS. So this tetramethylsilane has got four CH3 molecules attached to a silicon molecule. So all these four CH3 molecules are chemically equivalent. So since all four CH3 molecule are chemically equivalent, we get only one single NMR peak. So therefore, all these molecules, though the number of hydrogens are different, it gives only one signal. Fine. When we talk about let's see which organic compounds gives two signal. So the first example is the 2-methyl-1-butene. So you could see here is a CH3. CH3 is followed by a C double bond C and then a hydrogen. Similarly, here is also CH3 is connected to a C double bond C and then a hydrogen. But when we come to an opposite direction, hydrogen is connected to a C double bond C. So therefore, this hydrogen is also connected to a C double bond C. So therefore, this and this are chemically equivalent. So I'm explaining it again. So we have got two hydrogens this side. So this hydrogen 1 is connected to a C double bond C, and then it is connected to a CH3 this side. So hydrogen connected to C double bond C, hydrogen connected to C double bond C. So therefore this is chemically equal. And second thing is like, let's say like this compound. So this compound is CH3 attached to C double bond C. So therefore this is also chemically equivalent. So therefore in case NMR we'll have two spectra at a distinct positions corresponding to, for example, this will be, let's say like this is this one. So this will be corresponding to 6 hydrogen. If this is this one, then it will be corresponding to 2 hydrogens. So therefore the number of chemically equivalent protons each will have different number of signals. So similarly, the vinyl chloride will have 3 proton signals. Similarly, the 2 bromopropene. So because you see here the proton CH3 is attached to a C double bond C, and then this C double bond C is attached to a bromine. There is no other proton in the molecule which has got same chemical environment. Okay. The second molecule is that it is little symmetric in nature. So therefore, this hydrogen is attached to a C double bond C and then a CH3. Here it is attached to a C double bond C and then a bromine. So therefore, there are three different distinct hydrogen molecules or a proton molecule. Therefore, NMR will have 3 signals. So these are the chemically equivalent. So the number of signal tells us what is the different number of protons available in the system. In a molecule, we'll also call it also molecule. And the others are also very interesting examples. So here is an anion, which is called as a cyclopentadienyl anion. And sorry. So this cyclopentadienyl anion gives only one signal because all the 5 protons here are chemically equivalent. So similarly, cyclohexapentenyl heptenyl anion cation gives, there are also like 7 hydrogens here. On all the 7 hydrogens gives only one single peak. Similarly, benzene has got 6 hydrogens and all the 6 hydrogens gives signal at 7.4 delta. Okay, here we have got an aniline structure. So when we look at from the outer space, I mean, when we look at without looking into deep, you would see there all hydrogens are equal. But in case of aniline, it gives two signal. One is the outer electron. The second is the inner protons. Sorry, the outer protons and then the inner protons. So therefore, it gives two signal. So each molecule has got its own fingerprint kind of a spectra for a proton spectra so that it is very easy to distinguish between the number of equivalent hydrogens. In case of here, you could see there is only 2 equivalent hydrogens, but the number of hydrogens are almost like 16 number of hydrogens are here. In case of benzene, we get only one signal, but the number of hydrogens are 6. Whereas a small molecule like ethyl alcohol has got 3 different signals. So therefore, the number of signal corresponds to the number of the equivalent protons available in the organic molecule. So this is an the table in which it says what is the number of molecules or number of nucleus that are NMR active. In case of hydrogen, all 3 isotopes are NMR active, which is the proton, deuterium, and then the tritium. In case of carbon, only C13 is active. Only C13 is active, whereas the carbon 12 is inactive. In case of nitrogen, it is in case of nitrogen 14 as well as nitrogen 15, both are active, but the abundancy of nitrogen 15 is very low. What is abundancy? Suppose if it takes 100 atoms, if it takes 100 or 100 atoms, we would find 99.69% are or nitrogen 14. If we take and then it is just then 0.5 percentage, which is nitrogen 15. So because nitrogen 14 is the most abundant isotope. So similarly for the proton, hydrogen is the most abundant isotope. Deuterium is the very less available, and tritium is very difficult to find. Okay. So similarly, in case of oxygen, the 16 is inactive, whereas 17 is active, and then 18 is also inactive. So, and then the abundancy is 16 is more. So therefore the oxygen NMR measures oxygen 17 molecule. So in case of fluorine, it is F19 isotope, which is active. In case of phosphorus, it is 31, which is active. In case of chlorine, 35 as well as 37 is active, but the abundancy of 35 is more. Therefore, the most used isotope for the measurement of NMR is chlorine 35. So
Hello,
here we
doctor.
come. Yeah, yes.
Sorry to disturb you. You have like 10 minutes more.
Okay.
Okay, thank you.
So here is one example of the spectra. So this has got an, I think I'll move forward and go to a different example because, yes. So this is a substituted propane structure. So when we have a substituted propane structure, let's say that there are three different kinds of hydrogens present in here. Sorry, two different kind of hydrogen which is present in here. One is the CH3 we would see, and this is also CH3. And this CH3 is chemically equivalent to this CH3 because this CH3 is attached to a compound called as CHI. Similarly, the right side is also CH3 which is attached to this one. So therefore, both are chemically equivalent. So therefore, we'll have one signal. The second signal is the CH. You would see the CH is different from those. So therefore, this is the second signal. So here is the first signal and here is the second signal. And in case of NMR spectroscopy, there is a very important concept which is called as a splitting. So the splitting depends on the number of hydrogens present adjacent to the number of proton. In case of the first proton, in case of this CH3, let's say the adjacent carbon has got only one proton. So the splitting is the number of adjacent carbon plus one. For example, it has got one proton. Therefore, the splitting of this signal, this CH3 signal will be split into two. So we'll have one spectra like this, which will be split into two, which is similar to this. So therefore, the signal of this CH3 will be split into a doublet because of the presence of this hydrogen. Okay, and now, so as I said, the splitting is the number of depends on the number of adjacent protons to the molecule. And in case of let's say like this hydrogen has got, there are three hydrogens this side and there are three hydrogens this side. So therefore, total number of hydrogens are 6. So therefore, the number of splitting would be 6 plus 1, which is equals to 7. So one signal of like this proton will be split into 7 signals like 1, 2, 3, 4, 5, 6, 7. So this is called as a JJ coupling or spin-spin splitting. And this splitting occurs because of the presence of the nearby or neighboring hydrogen atoms in between them. Okay, so here is also a second example in which it shows the splitting. And this the splitting is very important because the chemical shift can be found in a small table, but understanding the splitting of the compound or the splitting of the spectra will help you to understand the structure of the organic compound. In case of this compound, you would see there are three different chemically different hydrogen atoms are present here. And this hydrogen atom, this CH3 has got only one hydrogen atom adjacent to it. So therefore, this peak will be split into a doublet. So here is only one hydrogen. So therefore, this will be split into a two spectra. Okay. In case of this, it has got a three hydrogen here and then one hydrogen here. So therefore, first this peak will be split into two, and then each of these two peaks will be split into 3 plus 1. So therefore, it will have a totally of 12 peaks. That is what it is given here. So since the 12 peaks, so it is split into 4 and each of this is split into again 2. So therefore, we have a different splittings because this hydrogen has got two different adjacent hydrogens. In case of hydrogen A, it has got only one neighboring hydrogen. Therefore, this signal will be split into two, which would be seen here. This is here. And therefore, as I said before, this CH3 will be split into two. So it is here. So the splitting tells us the chemical number of organic, so the number of hydrogens present in the adjacent to the compound. I'll quickly go through carbon spectrum. So carbon 13 spectrum. The carbon-13 spectra is not as difficult that of a proton spectra, because in case of carbon spectra, there will be no CC splitting. It just the different equivalent carbon will be shown as a different peaks. For example, this compound, all are chemically equivalent carbon. We are not talking about proton here. We are talking about carbon. So therefore, this will have only one peak. In case of this 5-membered ring, we have, sorry, 4 different carbons. So therefore, it will have 4 different peaks in between them. So this is a typical table in which it says like sp3 carbon will have a chemical shift around 4 to 45, and sp3 will have some 30 to 80. Therefore, C double bond C will have 100 to 40. So when we have propanol, yes, when we have a propanol, we would see that we have 3 different types of carbon, and each of this will be given in a different single line. So the carbon which is attached to a functional group, the carbon which will attach to a functional group will be highly upfield. So when we compare one single peak and then the chemical shift is increasing, this is called as an upfield. When chemical shift is decreasing, this is called as a downfield. So this third carbon which is attached to a functional group is upfield, and then therefore this CH3 which is away from the upfield is called as the downfield electron or de-shielded electron. So, and this is in spectra for the methyl acetate. So this methyl acetate has got 3 different carbons. So one is the CH3 carbon, second is the carbon attached to a double bond O, and also carbon attached to a single bond O. And we would see here the carbon attached to the double bond O has got more shifted towards the left side. So therefore it is around 170. And the one which is the methyl group is highly towards the 0. So therefore it is called as the downshift. And then the carbon, third carbon, which is the OCH3 carbon, comes around this one. So all these informations can be found in such a table, which will be a chemical shift table. So which will tell us the value in which, depending on the value, what is the nature of the compound or the organic. And similar to kind of carbon, we also have something called as phosphorus. So this phosphorus, depending on the structure, it will have a different position along it. And phosphorus will not have any splitting like that of a proton. So this spectra is just one single peak for phosphorus, which is attached to 3 phenyl groups, and this is called as a triphenyl phosphine. And similarly, when this triphenyl phosphine is substituted with a different organic compound, and here in this phosphorus is highly upshifted, which comes around 98.52. There is also something called as a different functional group can be found out from nitrogen NMR spectroscopy. So this is you would see that this nitrogen and this nitrogen is chemically equivalent. Therefore, the nitrogen NMR spectra of this will have only one single peak. In this, and nitrogen NMR can also be, we can also find out protonation and deprotonation. For example, in this example, when the pH is when the pH is high, the deprotonation occurs. So therefore, when it is a free base, this is a pyridine molecule and a substituted pyridine molecule. When it is a free base, the value is around 300. When it is a protonated base, the value is around 200. So therefore, the small change in the chemical environment can result in a big change in the NMR spectra. So therefore, NMR spectra is concentration sensitive as well as chemical nature sensitive. Sorry. And then this is an example of a fluorine spectra. So this is a substituted fluorine, and then depending on the nature of the fluorine substitutions, it will have a different spectra. And we would also see, I would also like you to observe this. It is like for phosphorus, nitrogen, and proton and carbon, it has a positive values. But whereas for fluorine, there are few compounds which has got a positive value and few compounds which have got a negative value. And this negative value depends on a standard which is called as a trimethylsilane. So there are also different forms of a NMR spectra, not just the proton, but carbon, nitrogen, fluorine, phosphorus also. So I think there is also something called as a 2D NMR spectra. I think this would be a discussion for the next session or future additional examples. So I think I would like to thank the faculty, the Ciencias Química, and then Dr. Sanal from FCQ for providing me this opportunity. And I will also like to thank UANL and then ECS, the student chapter from UANL, for helping me to present this. Also, I would like to thank the organizers and then the participants for such an active participating. Thank you.
Thank you so much, Dr. Vasanthakumar.
Yes.
So now we are going to have a question answer session for 10 minutes. And the participants can ask questions in the question answer session given at the top right corner. And there are already something like 3 questions.
Okay.
Doctor, I can read it for you. Can you please answer them?
Yes, I think, okay, please.
So the first question, I don't know the name of the participant who asked the question. It has 2 parts. The question is, can we use water as a solvent for NMR? If the compound contain carbon and if we are going for C13 NMR, which solvent we should choose? The solvent without carbon or with carbon? That is the question. Doctor, you are not audible.
Sorry. Yes. So the answer is like the first part of the question is, can we use water as the solvent for NMR? We cannot use water as the solvent for NMR. Why? Because if we use water as a solvent, the intensity of the water peak will be so high, and then the protons from the organic will be like at the baseline. So even when we use D2O, which is heavy water, so when we use D2O or a protonated solvent, the impurities of the water molecule present inside the solvent will have a very high peak. So therefore, using of water is not at all advisable because the intensity of water will be very, very high, and then the proton of your interest will not be seen at all. It will be very weak. I think the second part of the question is that, can we use water as a solvent for NMR? If our compound contains carbon, we have to go for C13 NMR. So for C13 NMR, the proton is not very sensitive. So, but still, to have we can use water in case of C13 NMR, but at least we have to use D2O instead of H2O. So in case of C13 NMR, the proton is not very important. So therefore, the solvent is also not very important. And then if the sample contains a carbon, and if you're not able to understand the structure just by analyzing the proton NMR, then it is very advisable to have a C13 NMR. Yes. Okay. The solvent with or without carbon is not important because carbon just gives a single peak. So therefore, it is easy to find out the solvent and then without the solvent, because there will be no solvent. I think there is no solvent without carbon. So therefore, it is not avoidable. So we have to use a solvent which contains the carbon.
Okay, I hope that answer is clear.
Okay.
The next question is, if my compound contain only carbon 12, not carbon 13, can I use NMR to characterize the compound? Compound has only carbon.
Yes, I understood.
12.
Thank you. Sorry, I am having a little throat infection.
All right.
Yes. And yes, I mean, there is a very good question. So I think like most organic compounds, we assume it has only carbon 12. But the percentage of carbon 12 to carbon 13 is very, very low. Suppose if we take an organic compound, there has got a very small amount of carbon 13 inherently present to them. So therefore, if you have an organic compound which contains carbon, definitely it has also got carbon 13 isotope present inside them. So it is not that the carbon 13 is specifically prepared. You can take any organic solvent, any organic compound, it definitely has a percentage of C13 inside them. So which will be NMR active, and the NMR machine is going to measure only that isotope. So therefore the isotope, that's why I gave a table of isotopic abundance. So irrespective of a compound, it will have an isotope that is NMR active. So you can use it if your compound has only carbon.
Okay. The next question, the principle of NMR is same for all type of NMR. If so, why we have proton NMR and carbon NMR separately?
Correct. But the intensities in which the proton NMR is observed and then the intensities in which the carbon NMR is observed are completely different. For example, if I have to show, I'll just show you the one spectra. Okay. This is an NMR spectra for a proton NMR. You would see the proton NMR has got signal from 0 to 10 and typically it is from 0 to 13 or 15. It cannot go higher. But when we go for a carbon 13 NMR, you would see the scale is very different. So here the scale is from 0 to 200. So therefore, depending on the scale, we have to measure the instrumentation setup. So if the scale has to be only from 0 to, if I say from 0 to 12, it is very here. So therefore, all my signals of protons are very small here. So therefore, I cannot see it. So therefore, the instrument settings has to be changed. So the what do you call, the machine remains the same, but whereas the instrumentation settings, for example, in case of I said like carbon, I said it is from 0 to 200. But if you go for a proton, it is if you go for a phosphorus, it is from minus 150 to plus 200. It is not from 0 to 200 because the phosphines will have at around minus 150 and then the substituted organic substituted phosphorus will have around 200. Therefore, since the scales are very different, we have to use a different instrumentation technique or the instrumentation setup to measure each signal. So the principle is almost same, but the range in which it comes are completely different.
Okay. The next question is, do we have a database to compare the NMR results so that it will be easy to compare? I mean, he is asking,
I understand.
it will be easy to compare this value with dedicated database besides comparing to scientific journal.
I mean, there is no specific database, but there are also standard values for each of the functional groups. For example, let's say like I have got a CH3. So when I have a CH3 attached to a CH2, it doesn't comes in a precise value. It comes like an what do you say, like for the XPS. When we talk about an XPS or an IR spectroscopy or an XRD, we talk about a range of spectra. We don't talk about a single value. So similarly, NMR also we have got something called as a standard table. So I would show here. So this is a standard table for a chemical shift for C13 NMR. So when we have a C13 NMR, the range is from 5 to 45. When we have a C double bond C, and then the carbon peak will come from this. So these are the standard values in which is available in almost all NMR organic books, or you can also refer the standard journals. But because of this standard values, we can assign each chemical structure to them. So there is no database available since it is a standard technique and the value is always in a range. It is not in a particular value.
Okay. And one more question. Can we use acid like acetic acid as a solvent for NMR?
We cannot use acetic acid as a solvent for NMR. Yes. Why? Because that is why we were talking about something called as a nuclear spin. So the sample should have only the nucleus or the protons of our interest. Let's say I have a methanol and then I add an acetic acid. So then you will have a peak for both methanol and then the acetic acid. So let's say like I have a small benzene. I have a benzene and then I add acetic acid. So that is why we use specific solvents which does not have proton. So I have discussed around 5-6 solvents like chloroform D, DMSO, D6, D2O. Even with water, we use a solvent without hydrogen. So therefore, the hydrogens has to come from only the sample of our interest or the test sample, not from the regular samples. So that will create a mismatching of signals. So therefore, you will not be able to distinguish your signals with the solvent signals. So only protonated solvents are advisable for using to use it for NMR.
Okay. Now this question is from Maren.
Sorry, deuterated solvent. I'm extremely sorry. Only deuterated solvents are advisable to be used for NMR.
Okay. So a question from Maren: how neighboring hydrogen affect the splitting of signals, though neighboring is still hydrogen? And why there is a high peak and low peak for hydrogen present in the sample material?
Okay, so actually I was not able to explain in detail about the splitting of them. So I would go here. Yes. So when we have a hydrogen, so let's say like when we have a hydrogen, we have something called as a electrons. So I have a molecule and then this is called as a shielding and then the chemical shift. So the splitting occurs because of the shielding effect and then the spin-spin coupling. Maybe I think I will. Okay, go here. So this is different types of hydrogen that can be available in a neighboring compound. So one is that geminal coupling, which means that a hydrogen is attached to a same compound and it is two different chemically to different environment. Or the easiest way to understand is this one. So what happens is that the number of hydrogens present inside them, the magnetic field of the adjacent hydrogen affects the neighboring hydrogen. So because of this reason, there is a splitting happening, and this is called as a spin-spin coupling. So because of the spin of the both hydrogens are in range, so they interact with each other, and because of that, the splitting is happening. And this is called as an spin-spin coupling or JJ coupling. So this is a term called as coupling, so which is responsible for the splitting of the peaks. So I think the spin-spin coupling is also a deep dive, so it will take, I mean, hours to explain, to go into detail. I think if you read something about spin-spin coupling or JJ coupling, you will be able to understand why neighboring hydrogen still affects the hydrogen, because though the magnetic fields are same, it is going to affect the magnetic field of the neighboring hydrogen.
Okay, doctor, thank you. One question from Guna. My polymer have to dissolve in hydrochloric acid in order to form a clear solution. So that how can I distinguish hydrochloric acid peak from my spectra?
I think like so when we talk about organic molecules, you would see that it is a proton. When we talk about a hydrochloride, it is called as just the proton. So you will not be able to see any peak of hydrochloric acid, I mean, of your polymer if you dissolve it in hydrochloric acid. So I think the best solvent I would suggest is try to use hexafluoroacetic acid. When we use hexafluoroacetic acid instead of HCl, because hexafluoroacetic acid can dissolve most of the polymers, or fluorine substituted, like for example 6-fluoro-isopropanol, 6-fluoroacetic acid, so trifluoroethanol. All these fluorine compounds can help you to dissolve your polymer, and you can do an NMR measurement. And using of HCl is not advisable for measuring NMR because it does not have a deuterated solvents to exchange. Second, it can also corrode your sample. I mean the NMR tube. It is also difficult to handle in case if there is a small breakage of NMR tube, and then it would destroy most of your electronics inside the machine.
Okay, we have some more questions. Let me read one question from Ananda Ganesh. Can we use NMR to analyze the solid electrolyte interface in batteries?
Exactly. So we can use the solid electrolyte can be used for, but in case if it is a polymer, you will have to dissolve it in a specific solvent. But there is also a technique called as a solid state NMR. So therefore, you can just use the solids to measure the NMR spectra without using a solvent. But that solid state NMR measurement is very kind of a time consuming project, I mean process. For example, the liquid proton NMR, we can measure it in 7 to 3 minutes. So 3 minutes is the shortest time you can measure, and then number of scans you can go in 3 minutes is like 12, 15, 24 scans. But in case of solid state NMR, to measure one sample, you would be requiring 3 to 4 hours of samples because it is a solid state. So therefore, the solid electrolytes, without even being solid, I mean without you need to change into a form of a liquid, you can also measure a solid state NMR for the electrolyte interface in batteries.
Okay, we have 3 more questions, Doctor. Do you have
Yes.
time?
Yes,
Okay.
maybe if you want me to read it, I can.
No, I will read. What about non-polar compounds? Are there any suitable solvents for that as well for NMR? How
Yes.
can you analyze non-polar compounds?
I think like I mean the non-polar compounds like for example DMSO D6 will help you to dissolve it. There is also like even some cases like D2O will also help you to dissolve the non-polar compounds. In some cases, we can also have a mixture of solvents like the acetone, we can have mixture of solvents like the deuterated acetone, deuterated chloroform, and DMSO D6 to have the to soluble the non-polar compounds. So it would be easily soluble when we mix the solvents.
Okay. So I will read the last question. Could you please explain anisotropic effect in annulenes?
Yes, I was not able to explain it is in this presentation. So this anisotropy arises from this is called as an aromatic deshielding and anisotropy. So this there is called as an electron ring present in an benzene ring. So benzene is a very small molecule that will help us to understand the aniline also. So in case of a benzene, what we have here is an electron current. So we know there is a number of pi electrons. So this number of pi electrons are surrounding the benzene. So therefore, the applied electric field, applied external electric field, some of this electric field is used, sorry, so applied magnetic field, some of this magnetic field is used to compensate the what do you call the pi electron cloud. So because of that, the protons in the pi electron cloud feels a stronger magnetic field. It says like it feels a stronger magnetic field. So that is the similar case when we talk about aniline also. I'll go here. So I think I was ever. So similarly, this is in structure of aniline. So when we have a structure of aniline, this pi electron cloud. So there is a pi electron cloud here. So so because of this pi electron cloud, there arises something called as an anisotropy. So anisotropy is different chemical environment. So in the same molecule, if we have two different chemical environment, so this is called as an anisotropy or ununiform nature. So ununiform nature of two protons are available because of the pi electron clouds. So here we have some pi electrons. So therefore, those protons which are outside the pi electrons are in a different chemical structure, which is highly deshielded. You would see you would have a zero here, and then this is the outer electrons is in the nion, and then the inner electrons are highly shielded. So therefore, it is in the negative side. So because of the pi electron cloud, there arises an ununiformity. This is in terms called as an anisotropy. And because of this anisotropy, there is a two types of signals in the aniline. Yes.
Okay, doctor, thank you. And we have one more question. I think you can summarize the entire session by answering this.
Okay.
The question is, if we have an unknown organic compound and its NMR spectrum is unknown, I mean, you have an NMR spectrum of an unknown organic compound, what steps would I take to identify the compound?
Yes. So I think yes. So this is the aim of the presentation. Actually, as you said, I can summarize the whole thing of it. So I think this slide tells the answer for it. So most NMR spectra are unknown. So whenever you develop an organic compound or you take an organic mixture and then try to measure an NMR, there people are now developing a database, and accessing to that database is also now difficult. But what we can do is just the 4 points. One, you would find the number of signals. Second is the position of the signals, and then the intensities of the signal. These three. So comparing all these 3 points will help you to arrive at a spectra 90%. So you can by using only these three parameters, we can arrive at the structure of the unknown organic compound. And then with the splitting, you can know what is the position of hydrogens that are present to the adjacent compounds. So therefore, it will be helpful for us to understand the structure of unknown organic compounds, even though you do not have an previously reported database or not. But to access this number of signals and position of signals, so there are various databases, for example, like this. Sorry. Yes, like this. So you will have a different kind of a database, which is a chemical shift table for a proton, for carbon, for different functional groups. We have got something called as a chemical shift table. So with this chemical shift table, you will be identified. Let's say like I have got a peak for CH3. If it is at around 4, I will know it is attached to a fluorine. If it is around 3.4, it is attached to a OH functional group. So because everything is a CH signal, CH3 signal. So, but this CH3 signal differs by what is the atom attached to it. So therefore, depending on the chemical nature of the compound or the chemical attached or the atom attached to the CH3 functional group, by understanding this table, I will be able to find out what is the functional organic group that is present. So therefore, I'll be able to construct a structure. So therefore, first find the number of peaks, position of peaks, and then the intensity, and then the splitting. So by following all these 4 steps, one will be able to understand the structure of the organic compound.
Okay, doctor, thank you so much. I hope we have answered almost all the questions that have asked